So for the new year, I thought we should go back to the roots of this channel and do something much more fun than my past few videos. This is a science video about quantum mechanics. If you watch a lot of physics videos, you've probably heard of this one. So in the 1800s, people realized that objects emit radiation with a range of frequencies that's dependent on its temperature. To model this behavior, which was observed, the first approximation was the Rayleigh-Jeans approximation, and it looks like this. So this worked well enough for longer wavelengths, but as you can see in the equation, for shorter wavelengths, this is going to go to infinity. And this equation is used to describe how much radiation is given from black bodies. So this being the solution implies that black bodies should radiate an infinite amount of energy. This is called the ultraviolet catastrophe because as you go shorter wavelengths, like in the UV, there's a catastrophe. The theory does not describe what we actually observe. We don't actually observe things emitting an infinite amount of energy. That doesn't make sense for energy conservation. That breaks thermodynamics, and it's not what we see. If the theory doesn't match what we see, the theory is wrong, right? Rayleigh and Jeans, they knew that this was wrong. They're just like, here's what we have. Here's what we think. And Rayleigh, is it Raleigh? Rayleigh? Lord Rayleigh? Is that right? Right? Rayleigh-Jeans? I would say Raleigh-Jeans. It's fine. Rayleigh suggested that because this theory was using something called the equipartition theorem to derive this equation, perhaps the equipartition theorem just doesn't work past a certain wavelength. Like the wavelengths are too short, the equipartition theorem must not apply, which means something is wrong with the physics there. Jeans suggested that the reason this thing breaks for short wavelengths is that it's because you don't take into account the ether. Is it luminiferous? Is that what they say? You don't account for the ether, and it's messing everything up. If we accounted for the ether, then it would work. But just look at this plot. If something is able to emit in the UV, it's going to emit infinite radiation, and that just doesn't make sense. The theory doesn't match the observations. We have a problem. So in 1896, Wien, of Wien's law, that's what we're talking about right now. If you're taking the physics GRE, just memorize that real quick because there will be a question on it. Wien tried to look at this problem from a thermodynamics angle, and he made an argument from these solids being made up of particles, which will have a distribution of energies, a Maxwell-Boltzmann distribution of energies. Since higher energy atoms are less likely to be available according to the Maxwell-Boltzmann distribution, Wien's law actually matches much closer to what we observe at shorter wavelengths and higher frequencies. However, Wien's law fails at low wavelengths, which if it fails to match what we observe, it must be wrong. So that means people were using Wien's law on one end and the Rayleigh-Jeans equation on another end and kind of meeting where they agree. And also, this is still classical mechanics. And the solution to this problem, the solution to the ultraviolet catastrophe is with quantum mechanics. In 1900, Max Planck knew the success of Wien's law and he wanted to improve upon it. He wasn't very happy with the thermodynamics derivation that Wien took. Max Planck took the data, he knew what we should expect, he knew what we observed, and he took Wien's derivation and he kind of worked it together until he got math that worked. They call this heuristically. And what happens is kind of amazing. To get the math to work, to get an equation that matches the observations, Max Planck takes this leap. And he says, if we assume that there's a minimum amount of energy that can be exchanged, this whole problem goes away. Here's the equation. Here's the plot. It works out. It matches the data. That minimum amount of energy is a quantum of energy. That's Planck's law. It matches Wien's law at longer wavelengths. It matches the Rayleigh-Jeans approximation at lower wavelengths, and it matches all the data. It is correct. Let's just pause here to think about this, how amazing it is that he found this, because why would you ever assume that energy is quantized? Isn't it weird? There's a minimum amount of energy you're allowed to exchange. Like, you can't go under that. And because you can't go under that, that means that the ultraviolet catastrophe goes away because those guys are not emitting energy because they're super high energy. We as human beings live in a world and we pretty much experience it classically. We experience it as continuous. But an understanding of underlying quantum mechanics, knowing that things are quantized, is required to describe observations accurately, to make predictions accurately. You look at a star, it's a macro object, but to understand why it is emitting radiation the way it is, you need an underlying understanding of the microstates of that macro system. You need to understand it on a quantum mechanical level, or you don't understand stars. That's so wild. And also, I'm like skipping a bunch of stuff here. Like, Kirchhoff had a lot of work on this. Stefan and Boltzmann worked on this, but I just skipped right to Planck with the answer, because that's where the quantum mechanics happen. So what's interesting is that Planck thought of this as like a mathematical tool. Like, it works if you consider the idea that maybe energy is quantized. But of course, Einstein is like, hang on a second. What if that's just true? What if that's just an actual thing? And then, quantum mechanics explode. Heisenberg and Schrödinger and Bohr and Dirac, all working on this new idea of quantum mechanics, this new idea that energy is quantized. And now we look back and we think, oh, Max Planck in 1900, Planck's law, this is the first quantum thing. This is the first time we noticed that quantum mechanics is required. And that's really interesting. What I also find interesting is that we had been observing effects of quantum mechanics, like spectra. Kirchhoff and Bunsen in the mid-1800s were like, every chemical has a unique fingerprint. When you look at what it radiates, you get these spectral lines. You get this emission spectrum and this absorption spectrum. That's because of quantum mechanics. That's because every chemical element has its own structure of protons and neutrons and electrons, and it has its own allowable energy shells. So therefore it has a unique chemical fingerprint. That is quantum mechanics, but we didn't know that was quantum mechanics. And you can go back even further to 1814. Oh God, I always say his name wrong. Fraunhofer, the guy who looked at the spectra of the sun and was like, whoa, look at this emission spectrum. This is interesting. And he started documenting all these lines only for Bunsen and Kirchhoff to go like, oh, that just tells us the chemical makeup of the atmosphere. All of those things are because of quantum mechanics, but we weren't aware of quantum yet. And once we become aware of quantum, that's why there's this huge explosion in physics knowledge, because this new idea just clicks and it explains everything. And we can replace all of our classical mechanics ideas with this new and improved quantum mechanics. I hope this isn't too loud. So this is a fun little physics demo. I have a Tesla coil, which means I have a high frequency changing electric field. And I also have these little ampules of gases. So what's going to happen is that a changing electric field will cause these particles of gas to move around and it will ionize them, which means, hopefully this works, they light up, right? And oh wow, the color looks super different on camera. That's interesting. It's kind of purpley in my hand. That's cool. So what's also interesting is that these guys will change color depending on what... Oh, these look so identical though. What I'm looking at, this is yellow and this is blue. That's okay. The color emitted by these gases after they're ionized will depend on the chemical makeup of the gas inside the guy, and hopefully some of these color differences will pick up on camera. So here's nitrogen. This one is bright pink. Oh, you can see how pink it is on my finger, but I don't think you can see it in the camera, and boy do they get hot. Oh, it's kind of cool. You can see the scale of the field. This is quantum mechanics, right? the proton, neutron, electron makeup of each of these gases is different, which means that the shells of energy are different, which means the amount of energy quanta the electrons in this gas can exchange is going to be very specific to the system. This is the same thing as spectra. I just find it really interesting. I kind of hoped we could just move this pretty close. Oh, you can see some of them. These are very small though. Hang on, I have some bigger tubies. Oh, there we go. So this is neon. This is xenon. Can you guys see the different colors? Helium, argon, and krypton. And so this is just ionizing the gases, so they're continually going up in energy level and emitting some light. And these tubies get really hot because it's like a little plasma inside, and plasma's hot. Is it technically a plasma? I think so. Anyway, yeah, so this is quantum mechanics. Fun. So physicists use words like quantization to describe the process of taking a classical system and mathematically describing it in quantum mechanics. So you take things that classically would be called point particles and you model them as wave equations. You could use the Schrödinger equation, for example. You have a system of n particles and you know all of their wave functions. You did a quantization. The Heisenberg uncertainty principle also gives us a clue of what we can quantize. Energy can be quantized, position can be quantized, momentum can be quantized. Time, whether or not time can be quantized, is an open question out of the scope of this video as well. Cool. That's how you quantize something. You take something classical like a proton and you describe it by its wave function. It is now quantized. What if you want to quantize again? A double quantized. So second quantization was a thing that was predicted mathematically before it was developed. We did first quantization, and we took our particles and we described them as waves. A kind of classical approach to a quantum mechanics problem. It was imagined that in order to go further, to remove some symmetries that popped up, because like one thing that happens when you quantize something is that if you have two particles and you switch their positions, you have a symmetry in your solution that you have to remove. But particles are indistinguishable, right? So it was imagined that in order to go further, in order to do more quantum, we would have to take a second quantization. But we didn't. Instead, the name second quantization just kind of sticks around, and second quantization is used to describe a situation where you take a field and you quantize it. This is taking your problem and making it more accurately represented in quantum mechanics. You have quantized particles and now you have quantized fields. However, this increases the difficulty of the math by a lot because under first quantization, you have a limited number of degrees of freedom. You have a countable number of degrees of freedom. And when you do second quantization, you have a very large number of degrees of freedom, perhaps an infinite number of degrees of freedom, which means there's just a lot more math. It's much more complicated to do. I'm so sorry, but I'm avoiding saying things like Fock space or creation and annihilation operators just because I'm trying to give the broad idea of what quantum mechanics is without getting knee deep in it, because this was supposed to be a fun video. But second quantization is a misnomer. You're not quantizing again. You're quantizing something different. And sometimes people call it configuration space instead. But second quantization accounts for the fact that particles are indistinguishable. So in second quantization, you would say something like, I have this many particles in this state A, and I have this many particles in this state B, and I have this many particles in this state C. So it's a different, more complicated way of solving the problem, but it's closer to being all quantum mechanics, instead of like classical mechanics with quantum stamped on its forehead, if you know what I mean. But what I find really interesting is that for most cases, the vast majority of physicists don't go as far as second quantization. You just don't need to. When you look at the world, a lot of the quantum mechanical effects are kind of washed out because we're looking at macro objects. So first quantization is just enough to do most things. It's not all the way to the correct answer, and second quantization probably isn't either, right? But first quantization, like understanding enough quantum mechanics, is enough to make predictions about the world. And I find that really interesting because, by the way, classical mechanics, which is incorrect, was also good enough to do a whole lot of things. Like all of thermodynamics is classical mechanics and it's perfect. Something like magnetohydrodynamics is a classical theory, but it works really well and we still use it. It's just interesting. Like quantum mechanics is underneath everything, but sometimes we don't need to know about it. But in cases like black body radiation, we definitely do. So anyway, quantum mechanics is a very successful theory of physics. And it has this recursive definition of like, oh, you quantize something by describing it in quantum mechanics. So when you think of quantizing something, I think the easiest thing to do is go back to the ultraviolet catastrophe and think of like the smallest amount of energy you're allowed to exchange. Like you have a bunch of energy, you break off the tiniest nugget and you're like, this is the limit. This is how much energy can be exchanged. It's important to quantize things into the smallest amount that's allowed to happen. That's quantum mechanics. I like it. I think it's interesting. Sorry, I don't know if you can tell, but I'm wearing a shirt that says quantum, quantum, quantum. This is merch. It's a really comfy sweater. I'm wearing a size large because I like an oversized sweater, and you can pre-order it at the link below. If you would also like to wear a shirt that says quantum, 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 because it's everywhere. The quantum, quantum, quantum. This is embarrassing to do, but like I really like the shirt, so follow your heart. You don't have to. It's totally fine. These are so small, I thought it would be kind of funny to have my Marie Curie doll hold it for me. Like, oh look, I'm Marie Curie. I'm Polish, not French. Haha, holding Mercury. That's appropriate. I'm Marie Curie. I've also got Rosalind Franklin. What element would she hold? That's such a great question. I'm gonna guess nitrogen. Because of her whole situation with the DNA. So there we go. There's Rosalind Franklin just holding some nitrogen. Does it take a while to... Is nitrogen broken? Did my ampule explode? Let's see. There we go. It's kind of purpley. There you go, Rosalind Franklin. Hold the nitrogen. Guys, I'm actually not doing okay. Things are gonna get weird. Is anyone else just like not having a good time? It's James Clerk Maxwell. He's Scottish. He's gotta choose his own fate. What would James Clerk Maxwell have? I don't know, you just did electrodynamics and heat. I mean, all of this is related because you did heat, right, James Clerk Maxwell. Let's do chlorine, why not? Haha. No! Hold the chlorine. Ooh, alright, this is rough. Oh my god, he's found us.